Hello, this lecture is continuation of Piezo transducers. So, in this lecture, we will discuss about the circuits used for piezoelectric transducers. So, from this picture, it is clear that this is the transducer, which is the piezoelectric transducer, and we are assuming that the piezoelectric transducer is experiences a force in the in a compressive manner. That means the force is going to be applied from top as well as bottom. The corresponding change that is going to happen in the dimension is like delta x, and because of this force, there must be some potential or the voltage will be developed, and this voltage has to be amplified by the help of a high impedance amplifier. The reason is piezoelectric transducers, the output impedance is very high, so we need to have an amplifier that should meet the impedance matching requirement. That's why we're supposed to use a high impedance amplifier. We can set the amplifier gain according to our requirement, and hence we can expect a corresponding output voltage. This output voltage can be used for the other signal processing applications. Now, if we see the equivalent diagram of the above circuit, this is a model which uses the charge model, where the charge equivalent to the transducer is represented as Q is equal to KQ into delta x, where delta x is the corresponding displacement, and RP, it is the leakage resistance, already we discussed in the last class. CP is the capacitance of the transducer, and Cc, because of the cable or the stray related, some capacitance related to the cable, or it also can be considered as some of the stray capacitance. Ca is the capacitance of the amplifier, and Ra is the resistance of the amplifier. So then the final output voltage is V out. So the circuit is further can be reduced by using an equivalent diagram. So in this case, we are going to combine the capacitors, since all the capacitors are connected in parallel. So we will find the equivalent value C, which is Cp plus Cp plus Ca plus Cc, three capacitors which are connected in parallel, and Rp and Ra, they are connected in parallel. Therefore, the corresponding equivalent is R is equal to Rp times Ra divided by Rp plus Ra. Therefore, the above circuit become much more simpler. In this case, the current circuit is, the charge circuit is going to be replaced by Ic times R. Then Ic is the current through the capacitance, and Ip is the current through the resistor. So it's become a RC parallel circuit. So in this case, we supposed to derive some relations. So Q, already we know the charge which is developed across the piezoelectric sensor, that is given by KQ into Xi, where KQ is a constant and Xi is supposed to be the displacement because of the external force or the pressure. And if we try to find out the dq by dt is something but rate of change of charge, which is something but current, so which is equal to ICR. ICR is the current. That is equal to KQ into dxi divided by dt, because KQ is a constant and the only variable is xi. So the total current ICR, that is equal to IC plus IR, where IC is the current to the capacitance, whereas IR is the current to the equivalent resistance. And the output voltage is either voltage across the R or voltage across the capacitor. So in this case, we are just assuming that voltage across the output voltage is equal to Vc. So we'll get equation of current through a capacitor 1 by C into integral I dt. That is the basic standard equation. 1 by C into the current through the capacitor is Ic dt. So 1 by C times Ic is the current through the capacitor, which is something but the ICR minus IR. So ICR minus IR times dt. So now dV0 by dt, the rate of change of voltage across the capacitor, or the output voltage, change of output voltage with respect to time, that is equal to, if you differentiate this particular term, this integration term will disappear. So 1 by C into ICR minus IR. So if you rearrange the equation, the C, if you move to this side, we will get what? C dV0 by dt is equal to ICR minus IR. As you know, ICR from the previous equation, KQ into dXi by dt, minus IR is the current through the resistance. It is nothing but the output voltage of the V0 divided by R. So if you further rearrange this equation, if you can just move this V out of R to the left hand side, C dV0 by dt plus V out by R, that is equal to KQ into dx divided by dt. And just multiply this equation on both sides by R. So we will get RC dV0 by dt plus this R will get cancelled. We have V0 is equal to R KQ dx divided by dt. So RC is the time constant of the circuit. So if you replace this RC by tau, so tau into dV0 by dt plus V0 and that is equal to, just replace R by RC. So in order to balance it, you have to divide by C. So this RC is going to be again tau dxi divided by dt. So if you simplify further, tau dV0 by dt plus V out, that is equal to this KQ by C, we are going to make a new constant which is K. So this has become K times tau dxi divided by dt. The value of K is called the sensitivity of the piezo transducer, given by KQ divided by C. The unit is volts per meter. Now we will try to apply the Laplace transform on both sides of this equation. So if you apply the Laplace transform, tau is going to be constant, this is tau. Derivative of the Laplace transform of derivative of a function is given by s into f of s minus f of 0 plus. So f of 0 is the initial condition. So if we just forget about the initial condition or neglect the initial condition, or we assume that the initial conditions are 0, then the above equation becomes tau into s VL of s plus VL of s, because V out will be VL of, or supposedly this is V out of s. This is also going to be V out of s. So tau into s V out of s plus V out of s, that is equal to K tau into s into x of s. Here also the initial conditions will cancel or mean